Hello again, lovely chemistry students. It is going to be a lovely night tonight with Indy because you get to learn some more about chemistry. So I just finished recording the video on oxidation states and introduction to redox reactions. So now we are going to be moving on as to how to balance redox reactions. So let me pull up the slideshow. Sorry if it's a weird background right now. I wasn't ready. Okay, now I'm ready. All right, so we are going to start off with a discussion of what a redox reaction is and what half equations are and how they can be used to write and balance full redox reactions. Okay, redox reactions, when you balance them, are a little bit different than just balancing a normal chemical equation because redox reactions involve the transfer of electrons. So you have to add in the component of how to balance the electrons in terms of what is being oxidized and reduced because you have to have an equal movement of electrons on both sides of the equation. And because it can be difficult to see what's being oxidized and reduced when you write a full chemical equation, oftentimes you start out by writing what's called a half equation in a redox reactions. So half equations just show the oxidation step separate from the reduction step. So for example, we have hydrogen and fluorine reacting to form hydrogen fluoride. So instead of writing it like that, because we don't exactly know how many electrons are being transferred in this reaction, we write the half reaction or half equation for what's being oxidized and what's being reduced, and then combine them to write the full balanced redox reaction. So the first thing you want to do is identify, okay, well, what is oxidized and what is reduced? So hydrogen and fluorine are both in their diatomic natural states, so they have oxidation states of 0. Then in hydrogen fluoride, the hydrogen has a +1 oxidation state and the fluoride has -1. So you can see that the hydrogen is being oxidized and the fluorine is being reduced. So because of that, you can separate them out into what's called half reactions. So you take the hydrogen and you write what it forms as an ion. Okay, so and that's because it's being oxidized into hydrogen +1. And because there are two hydrogens, because it is diatomic, that means there have to be two hydrogen ions on the product. Likewise with fluorine, it is diatomic, so it forms two fluoride ions. So after you write those half reactions, you want to say, okay, well, it's going from 0 to +2 for hydrogen or 0 to -2 for fluoride if it's balanced. And of course, you want to balance the number of atoms on both sides. So you're dealing with a movement of 2 electrons. So because of that, and you know hydrogen is being oxidized, you're going to put the electrons on the product side because it is releasing electrons. And in the case of fluorine, it is gaining those 2 electrons to form the 2 fluoride ions. So the hydrogen shows the half reaction for oxidation, and the fluorine shows the half reaction for reduction. And you can do the same thing here. You can write the half reactions for these if you want to try it out and check your work. But now we're going to move on from the half reactions as how we use that to write full balanced redox reactions, and also how we have to usually do these reactions in acidic or basic solutions. Now, IB doesn't require you to know how to balance redox reactions for basic solutions, but they do require you to know how to do it for acidic solutions. So if you click this link here, it actually takes you to a step-by-step instruction as to how to balance redox reactions. So we are going to click on this so I can show you. Okay. An example of balancing a redox reaction. Okay, so like I said, the first step is identifying what's oxidized and reduced and splitting them into half reactions. Then what you're going to do is you're going to balance each half reaction, everything except the hydrogens and oxygens. If you can't get the hydrogens and oxygens to balance, don't worry about it until the end. Then in order to get them to balance, you're going to either add water to balance the oxygens or hydrogen ions to balance the hydrogens. And you put the hydrogen ions there, so it's an acidic solution. And because you're dealing with a solution, it's okay to add water on the other side. And of course, you're going to make sure your electrons are balanced in your half reactions. You are then going to make sure that both your half reactions have the appropriate number of electrons. And sometimes you need to multiply the half reaction by a coefficient in order to make those electrons balance. That is also okay, as long as you multiply everything by that coefficient. And this is telling you how to do it if your solution is basic, which you don't have to worry about because you don't have to know that. But let's give an example, okay? So this is balancing this reaction in acidic solution. So this is permanganate and this is dichromate. Normally when you're dealing with redox reactions, you have these ions that are attached to spectator ions. For example, in permanganate, normally you have potassium permanganate or KMnO4, and for dichromate, you would normally have sodium dichromate. However, these are spectator ions. The potassium and the sodium are not going to really form any type of product that is relevant to the reaction. They just stay ions in solution. So because of that, we don't usually include them in the full balanced redox reactions, and IB does not require you to put the spectator ions in either, so you don't have to worry about it. Okay, so if you have this reaction, permanganate and dichromate make manganese and carbon dioxide, okay? The first thing you want to do is split them into their two half reactions by assigning oxidation state to each element and identify what is oxidized and what's reduced, okay? And if you do that, you're going to realize that the manganese over here in potassium permanganate, normally that has a +7 oxidation state, and it's going from +7 to +2 because remember our oxidation rules. Whatever charge is on that ion is the oxidation state. So it's telling you manganese has a 2+ charge here. So it's going from +7 to +2. So the permanganate is being reduced, therefore the dichromate is being oxidized, and you can assign the oxidation states to prove that to yourself, okay? So the first step we want to do is balance everything except for the hydrogen and the oxygen, right? We have one manganese over here and one manganese over here. I'm not worrying about the oxygen yet. For the dichromate, I have two carbons over here, and I only had one in the carbon dioxide, so I'm going to put a 2 in front of the carbon dioxide to balance out the carbons. Then what you're gonna want to do is worry about the hydrogens and the oxygens. So over in the permanganate half reaction, you can see that we have oxygen on the left, but nothing on the right. So to balance the oxygens, you're going to add water. And because I have 4 oxygens on the left, I need to add 4 waters on the right. So that makes 4 H2O. Then, of course, you have to balance out the hydrogens by adding a hydrogen ion. But let's look at the dichromate half reaction first. You can see this has 4 oxygens on the left and 4 on the right, so I don't have to do anything with that with water to balance it. Okay, but now to worry about the hydrogens. When I added the water on the right side of the permanganate half reaction, I added in 8 hydrogens on the right, so I have to add 8 hydrogen ions on the left in order to balance them out. Okay? And then we want to make sure to balance this by adding electrons. And sometimes I do the electrons first, sometimes I do it last. That's really up to you. But looking at the change in oxidation state, I told you it went from a +7 to a +2. Therefore, it must have gained 5 electrons. It was reduced. In the potassium dichromate, you can see here that the oxygen is -2, so that makes a -8 total charge, which means we have to have a +6 from the carbon because the overall charge of dichromate is a -2. So if I have a +6, that means each carbon has to have a +3 oxidation state here on the left. Then on the right, looking at carbon dioxide, carbon would have a +4. However, there are 2 carbon dioxide molecules, right? 2 carbons here, 2 carbons here. So instead of losing just 1 electron, it actually loses 2 electrons. And then we have a problem here, right? Because we have 5 electrons here and we have 2 electrons here. So to solve this problem, you actually are going to have to multiply the top equation by 2 and the bottom equation by 5. That way you can have 10 electrons on each side that balance each other out. Then when you do that, then you can add them all together and you have your full balanced redox reaction. Right, and of course you can try this. You can balance out these half reactions by adding water and hydrogen ions if you need to. But this tells you why a lot of the times in redox reactions you have to have acidic solutions because you can't make the redox reaction balance without it for many of these redox reactions. And whenever you do add them together in that final step, we didn't show the final step for the last example, but when you do add them together, this gives you the original net ionic equation. And it's a net ionic equation because it does not show any spectator ions. So you notice how we wrote the fluoride separate from the hydrogen ions and not hydrogen fluoride together because it can split apart into ions in solution. So that is how we show it in a redox reaction. Okay, so now we are moving on to how we can use redox reactions in order to figure out the concentration of an unknown solution in a redox titration. Formerly, we've been doing titrations with acids and bases, but instead of doing that, we're going to have an oxidizing agent or substance to be oxidized, so the substance is going to undergo a redox reaction. And then we're going to add an indicator in this titration that usually changes color depending on the oxidation state of a substance in your solution. We cannot use M1V1 equals M2V2 when we do titrations, okay? Why not? Well, for one, this is assuming the same substance, right? That's just a dilution formula. If you take one substance and you dilute it, yes, you can use that, but that's not what we're doing. We're doing a chemical reaction here where you are looking at stoichiometric ratios between things that are reacting. So this equation is not relevant when you are trying to do titration calculations. And sometimes indicators aren't needed in redox titrations because sometimes if something undergoes a redox reaction, it just changes color on its own. For example, if you have iodine, right? Iodine is a brown substance. When it gets reduced to iodide, it turns clear, so no indicator is needed. Same thing for methylene blue. Whenever it's in the presence of glucose, it undergoes a redox reaction and it changes color. These redox titrations are used in things like the food and beverage industry. It can be used to analyze for the presence of sulfites. We're actually going to be doing a redox titration involving sulfite concentration in grape juice for our last lab of the year. So that's going to be exciting. Because that's a redox reaction, they can analyze how much sulfite is in it. They can also analyze how much vitamin C is in foods. They can use it to determine the purity and content of certain substances in the pharmaceutical industry. So for a lot of the time, like if you're using an iron supplement, the iron can be oxidized to iron 2 plus to determine how much iron you have in your tablet. Can also be used in a water environmental analysis. A redox reaction can be used in something called the Winkler method in order to determine the concentration of dissolved oxygen in a solution. So the steps to finding the mass or the concentration of something unknown using a redox titration. Well, again, you're going to want to write out the two half reactions, make the full ionic equation, the balanced redox reaction. So after you have your full ionic equation, your redox reaction, what you're going to want to do is calculate the moles of your titrant that has been used to reach equivalence in your redox reaction. So instead of an acid-base reaction where the moles of substance that's in your burette, your acid or your base, is used to neutralize the analyte, instead we're going to be looking at where equivalence is reached. So when the redox reaction has reached completion. So if something in your burette, for example, iodine, and what if it's reacting with something, your analyte, in order to be reduced to iodide? Iodine is a brown colored substance and iodide is clear. So if something is in your analyte and it is reducing all your iodine, right? Whenever all of that substance that is doing the reducing, whenever that is used up, then your solution will go from clear to a light yellowish color because it has reached its endpoint. It no longer can reduce all that iodine to iodide, so you're going to have excess iodine in your Erlenmeyer flask, and you will have a color change when the reaction has reached completion. And what I mean by completion means there's no more substance in the analyte that is undergoing the redox reaction with the substance in the burette. You can then use the moles of the reacting substance in the flask in order You can then use the moles that it took to reach equivalence, and then using the stoichiometric ratio, you can figure out the moles of your reacting substance, aka your analyte, in the flask. Then you could work out the moles in your original solution, because you could have diluted something in your Erlenmeyer flask, so you have to, multiply by a ratio, a diluting factor, whatever. And then you're going to either work out the concentration by dividing by the volume that was in your Erlenmeyer flask, or your original volume of solution if you diluted it. Or you can figure out the mass of something by finding the moles and then multiplying by the molar mass in order to get the grams, or the mass of whatever it is you're looking for. And don't forget that the amount of solution that is added from the burette to reach equivalence is called the titer. So here are some equations for typically used reactants in redox titrations. Permanganate is a big one, because permanganate is a very strong oxidizing agent. So a lot of times it is used to oxidize other things. And then if it does, for example, with iron, it's very common to use it with iron to oxidize it. So ethane dioate can become carbon dioxide. So ethane dioate is a really strong reducing agent. So it reduces other things and becomes oxidized. And then iron always loses electrons, so it's a really good reducing agent. But it can go both ways around. Like you can have iron 3 plus be reduced to iron 2 plus as well in certain conditions. And then you have dichromate. You have dichromate, which is a very strong oxidizing agent, so it can oxidize other things and be reduced, and then this reaction can be utilized to determine the concentration of other things that it reacts with. So a really typical example, like I said, is reacting iron with potassium permanganate. Sometimes it's called manganate 7, because in potassium permanganate, the manganese has an oxidation state of +7. So an example is if you have a certain volume, 24.30 cubic centimeters, of a 0.010 molar potassium permanganate, you have that in the burette because you know the concentration of it, and you're reacting it with an acidified iron sulfate solution to form manganese 2 plus. So again, potassium permanganate is a really strong oxidizing agent, so it gets reduced. So it's oxidizing the iron. Anyways, so this was originally taken from a solution in a 250 centimeter cube flask. What was the original mass of the iron 2 plus in the iron sulfate? Okay, so how you start this can be a lot, so take it step by step. First things first, you will have to figure out the half reactions to figure out what's oxidized and reduced, and balance that to make your balanced redox reaction. So you have the potassium permanganate, and you know that it is reduced because it is oxidizing the iron in the iron sulfate. So it's being reduced from Mn +7 to Mn +2. And because of that, it is gaining 5 electrons. And if you balance this half reaction, you're going to see you need 8 hydrogen ions on the left, and then that causes 4 waters on the right. So this is again an acidic solution because you need that to balance out this redox reaction. Then you have your iron 2 plus going to iron 3 plus, but because you have 5 electrons being taken by the potassium permanganate, you have 5 electrons being released from the iron, so you have to multiply everything by 5 to make the electrons the same. Then if you add everything out, this is your balanced redox reaction here. Then what you're going to want to do is figure out the moles of your titrant that was used to reach the equivalence point. And it told you in the example problem that it took 24.30 cubic centimeters of 0.010 molar. So all you have to do is multiply your molarity by your volume in order to get moles of titer that it took to reach equivalence. Then you can use your balanced redox reaction just like we did in acid-base titrations in order to convert the moles of your titrant to your moles of analyte. And in this reaction, the permanganate to the iron is in a 1:5 ratio. So what you're going to want to do is multiply your moles of permanganate by 5 in order to figure out your moles of iron. And when you do that, you get 0.001215 moles of iron 2 plus. And because I told you that it was in a 250 cubic centimeter flask and we only titrated 25 cubic centimeters, that means really the amount of moles was 10 times as much because we only took out a tenth, right, of what was in the original flask. So I have to multiply that by 10 to get the moles of iron that was in the 250 centimeter cube flask. And then to get mass, you just multiply by molar mass of iron, and you'd say there was 0.68 grams of iron sulfate originally in your iron sulfate solution. You can also try this using a iron tablet, and it was converted to Fe2 plus. Okay, and then our last example, we are going to be using sodium thiosulfate a lot in redox reactions because sodium thiosulfate is a really strong reducing agent. It can oftentimes be used in the reduction of iodine, which I mentioned before, to iodide. So iodide plus an oxidizing agent will make iodine. So this isn't the reaction with sodium thiosulfate. So you want to make your iodine somehow, and once you have that iodine, then it can be titrated with sodium thiosulfate, and sodium thiosulfate could be in your burette in this case. You can actually do these titrations both ways. You can have either the iodine in the burette or the sodium thiosulfate in the burette, depending on what you want to do in this titration. But in this case, we are going to titrate with sodium thiosulfate in our burette, and then we are going to observe when all of that iodine, which is our analyte in the Erlenmeyer flask, has been reduced to iodide. So in this case, it's going to have something clear in the burette, and then something that's dark colored in the Erlenmeyer flask. Whenever that sodium thiosulfate completely neutralizes the iodine, right, it's going to turn clear to iodide. So a lot of the time when we're doing this type of titration, we use starch as an indicator. Even though the iodine will turn clear without the starch really helps make the equivalence point very distinct because starch will combine with any iodine left over, even if it's a small, tiny little amount, and turn it blue. So we might think that the solution is completely titrated, it's completely clear and neutralized, right? But then you add a little bit of starch and it turns a pale blue color, indicating there's still a little bit more iodine in your analyte. So you want to add a couple more drops of the sodium thiosulfate. So that's why starch is often used. In this reaction, the sodium thiosulfate, like I said, it's a really strong reducing agent. So it gets oxidized and it reduces the iodine to iodide. And so the color is going to disappear at the equivalence point. And like I said, it will form a deep blue color in the presence of starch, the iodine will. And so you know when your endpoint is reached because that blue color will fade out. Okay, so here's a typical sodium thiosulfate iodine redox reaction. So you say you want to make iodine. You want to react iodide with something called iodate in order to make iodine. The reason this is often done instead of just using like a store-bought solution of iodine in order to do this reaction is because you don't necessarily know exactly how much iodine is in your solution, and it's often can be unstable and degrade over time. So it's better to make the iodine fresh and control that yourself. So if you mix iodide and iodate, which is IO3 minus, together, you're making iodine, which can then be titrated with sodium thiosulfate like we just talked about. All right, so how do we make the iodine? So iodide can be oxidized to iodine. That's the half reaction here. And then the iodate can be reduced to iodide. So you can see that the iodate can be reduced to iodine. Both iodine is in the reduction and the oxidation reactions, which is a little bit different, but hey, that's okay because remember, iodine can have multiple oxidation states. It's a weird guy, okay? So looking here, if we have the two iodides, it is releasing 2 electrons, right? However, in iodate, the oxygen has a -2 charge, which means the iodine here in the iodate has a +5 oxidation state. And because there are 2 of them to balance out those 2 iodines here, That means 10 electrons are being gained by the iodate to make iodine. So iodide's losing electrons here in the oxidation reaction, but iodate is gaining electrons in the reduction reaction. And I told you that the electrons had to be balanced. So in order to do that, I have to multiply that top reaction by 5 in order to get 10 electrons to be balanced out. So, oh, I have electrons on the wrong side here. My bad, I'll fix that. Let me fix that. Okay, sorry about that. I fixed the electrons. Okay, so looking at the iodide reaction, I don't have any hydrogens or oxygens, so I don't have to worry about it. However, for the iodate reaction down here, I have oxygens here on the reduction half reaction, so I need to add waters to the right-hand side in order to balance out the oxygens. And because there are 2 iodates, I need to add 6 waters, okay? That makes 12 hydrogen ions that I need to add on the left. So combining the half reactions then gives me the 10 iodides and the 12 hydrogen ions, the 2 iodates, 6 iodines, and 6 waters. However, looking at all of this, you can see that they're all divisible by 2. So I am going to reduce it and get 5I minus plus 6H plus IO3 minus yields 3 iodine and 3 water. Now again, the whole point of this was to make iodine. And again, you need to have acidic conditions to make this happen. Otherwise, the iodine is not going to be produced, because you can see for this iodate, it's not going to balance out unless you have water, and then resulting, or accordingly, unless you have water and then also hydrogen on the left in order to balance out the hydrogen in the water. So here's a summary of basically what is happening here, okay? So we made iodine, right, using our iodide and iodate, and when we did that, we are then going to determine how much iodine is in that solution by reacting it with sodium thiosulfate. So the half reactions for the actual titration are these on this slide. This slide is just showing you how I made the iodine that I am then putting in the Erlenmeyer flask to titrate with sodium thiosulfate. Okay, so when I do that, I add the half reactions together to get this one here. And this is my balanced redox reaction for the titration. So this is the one I care about when I'm trying to use the stoichiometric ratios in order to figure out the concentration of iodine in solution. So here's my overall reaction. Again, you can see that the iodine reacts with this thiosulfate to make iodide and something called tetrathionate, which is the S4O6 2- here. So if you're doing this redox titration, right, and you have a certain titer of sodium thiosulfate, you can find the moles of sodium thiosulfate and then understand that it's a 2-to-1 reaction, or 2-to-1 stoichiometric ratio between sodium thiosulfate and iodine. So you would then divide this however many moles of thiosulfate by 2 in order to figure out moles of iodine. And then from there, you can figure out concentration. You can also try this type of titration yourself, looking at sodium hypochlorite, which is bleach, and figuring out the concentration of this sodium hypochlorite, or the OCl minus, in the bleach using a sodium thiosulfate titration. All right. The very last type of titration we're going to talk about is something called the Winkler method. It's literally the exact same steps, just using a different redox reaction. And in this case, we are going to determine the amount of dissolved oxygen in water. The reason that's important is because it is one of the most important indicators of water quality. If there is more pollution in the water, more bacteria, then that bacteria is going to be, decomposing, eating that stuff in the water, and it's going to be using oxygen as it does so. So because of that, polluted water has much less oxygen content than less polluted water. And this is called biological oxygen demand, which is the amount of oxygen used to decompose the organic matter in a sample of water over a specified time period. So basically what they do is they measure the amount of oxygen in a water sample, and then 5 days later measure it again in order to figure out what the oxygen demand of that water is. The more bacteria in the water, the higher oxygen demand and the lower oxygen levels. So if you have a really high BOD, that means low oxygen levels in the water. So if you have a BOD of 10 or greater, your water is very polluted with a lot of organic waste that is being decomposed. If you have a BOD level of 1 to 2, it is very good water quality. Moderately clean is a BOD of 3 to 5. 6 to 9 is, you're kind of polluted. And you can actually relate this to algal blooms, because if you have a lot of algal blooms in the water, they're going to be using a lot of oxygen, which lead to a larger biological oxygen demand and more polluted water. No, Indy, you can't come out. You're already out. Okay, how do we actually measure dissolved oxygen in water? Well, redox titrations are used to measure this because the oxygen can be fixed to a certain substance and then undergo a series of redox reactions in order to do a titration that you can determine the amount of moles used to neutralize or reach equivalence in that titration reaction, and then back calculate using stoichiometric ratios how much oxygen was in the water. So normally the first step is to actually put the oxygen in a fixable state. It's because oxygen's a gas, right? It's very finicky. It can dissolve out of the water. So you want to fix it to something, and it's normally fixed by the addition of a manganese salt, such as in manganese sulfate. It doesn't have to be manganese sulfate, but normally something with a manganese 2 plus charge. And then it's reacted in a basic solution. So this is an example of something that requires basic conditions to react rather than acidic conditions. But it will fix the oxygen to form manganese dioxide and water. And then what you're going to want to do is add acidified iodide ions. The reason it has to be acidified is because this redox reaction involves the reduction of manganese dioxide to manganese 2 plus, and in doing so it oxidizes the iodide to iodine. So if you balance out these half reactions, you would see that acid is necessary to make this work. And then once you have the iodine, we already talked about this, you can then titrate it with sodium thiosulfate to figure out at which point the sodium thiosulfate reaches equivalence and neutralizes all of the iodine in the solution. So from this, you can figure out, okay, what's my concentration of iodine? If you know your concentration of iodine, then you can, say, okay, well, what is my stoichiometric ratio between iodine and manganese dioxide? And then look at the first equation and say, what's my stoichiometric ratio of manganese dioxide to water? So it's kind of like a 3-step back calculation using stoichiometric ratios to get to the oxygen, which is what you care about. So what would you see visually when you do this reaction? Well, when you add the manganese 2 plus ions under basic conditions to a solution of water, it produces a pale brown precipitate. Usually it's manganese hydroxide. It doesn't have to be manganese hydroxide that you are adding to the oxygen. Like I said, it could be manganese sulfate. It doesn't matter as long as it's Mn2+. But in this case, we added manganese hydroxide. And when it does that, a pale brown precipitate will be produced. And then what you're going to want to do is react it with that acidified potassium iodide, which is going to then turn the solution, this manganese, in this case manganese hydroxide, it's going to cause that to be reduced, and then the potassium iodide to be oxidized to iodine. So it'll turn that more like yellow-brown solution to indicate that you're making iodine. Like I said, sorry, before, the manganese goes from +3 here to a +2, so it is being reduced while the iodide is being oxidized to iodine. And then you're going to measure the amount of iodine, like I said, with a sodium thiosulfate titration. So it's going to go from a brown or a yellow, depending on how much iodine is in your solution. You're adding your starch indicator in order for that iodine to turn blue, and then when you add a couple more drops of the sodium thiosulfate, it will turn clear, and to indicate that equivalence has been reached. Okay, so give an example of this. You have a 500 cubic centimeter sample of water, and you want to see how much oxygen's in it. So the first step, you're going to fix the oxygen with manganese 2 plus. So in this case, we again did manganese sulfate. You could use manganese hydroxide too, in basic solution in order for that redox reaction to balance out. After that, you're going to acidify it with potassium, or sorry, not acidify it. You're going to add acidified potassium iodide in order to make iodine. Okay? After that, you titrate the iodine with sodium thiosulfate. Those are the steps. And it took 12.5 cubic centimeters of 0.05 molar sodium thiosulfate in order to react with all of the iodine from that second reaction that was made. How can you calculate the dissolved oxygen? And I'm doing it in grams per cubic decimeter because that is equivalent to ppm, which is normally what dissolved oxygen is measured in is ppm. Okay, so it took 0.000625 moles because you multiply the concentration of sodium thiosulfate by the volume of your titer. And then, again, like I said, you want to like back calculate step by step. The sodium thiosulfate and the iodine react in a 2-to-1 ratio like I showed you before in this equation. So you're going to divide your moles of sodium thiosulfate by 2 in order to figure out your moles of iodine. Then, looking at our manganese dioxide and our iodine reaction, you will see that it is in another 2-to-1 ratio. Looking here. Where is it? There we go. So we use manganese sulfate in this case. So once you use your 2-to-1 ratio, you'll know how much iodine you have, correct? Iodine and manganese dioxide are in a 1-to-1 ratio. So the amount of iodine, the moles of iodine, is equivalent to the moles of manganese dioxide. And then we have 2 moles of manganese dioxide for every 1 mole of oxygen. So again, in a 2-to-1 ratio. So when you're trying to do this math, once you have your moles of manganese dioxide, you are going to want to again divide it by 2 because you're trying to get to moles of oxygen, and there's twice as much manganese dioxide produced as 2 moles of oxygen on the reactant side of that reaction. So again, dividing by 2 gives you moles of oxygen. Then to find mass, you just multiply by the molar mass of diatomic oxygen, which is 32, to get grams of oxygen that was in your 500 cubic centimeter sample, because that's how much water you collected. Dividing those two numbers, turning it to decimeter cubed, you get 0.0102 grams per cubic decimeter of oxygen in your water. So you can try it yourself using the same exact steps and try to figure out the concentration of dissolved oxygen in the original sample. And if they ask you and here's the answer to that in case you needed to know. If they ask you about BOD, so you'd have to know the amount of dissolved oxygen on one day and then 5 days later. So if the amount of dissolved oxygen goes down significantly, that can tell you about the biological oxygen demand of your water sample, and in turn tell you how polluted your sample is. All right, guys, that is it for this second lesson, and please let me know if you have any questions, and I hope you have a fabulous night. Bye. Oh, by the way, sorry. Milligrams per decimeter cubed is what ppm is in. So this is gram per cubic decimeter. So this would be 2. So this would be 10.2 parts per million of oxygen that is in this water sample. So yeah, sorry, it's milligrams per liter, or milligrams per cubic decimeter is equivalent to ppm. Okay, bye. In order to determine the content of iron in substances. In this case, the potassium permanganate, like I said, is oxidizing the iron in iron sulfate. So instead of iron and like in an iron tablet, it's actually oxidizing the iron 2+ in iron sulfate to iron 3+.